So section 4.9, page 119. What we're going to be talking about with this is how to figure out whether a function is linear, quadratic, cubic, or even quartic. So we're going to be given a bunch of data points. We want to know, what type of data do we have? Is it a linear function? Is it a quadratic? Is it a cubic? Is it a quartic? We can't waste all our time putting in the data and just keep checking. So I'm going to show you some ways we can find out that answer. So the first thing is just this vocabulary term and finite differences. It says the differences of consecutive values when the x values in a data set are equally spaced. Okay, and we got that? So the properties of finite differences. If a polynomial function has degree n, then the nth differences of the function values for equally spaced x values are non-zero and constant. I'll show you what we mean by that here in just a minute. Conversely, if the n differences of equally spaced data are non-zero and constant, then the data can be represented by a polynomial function of degree n. Okay, doesn't make a lot of sense when you listen to it that way, but it will once we do a couple of examples. So let's look at this first one here. It says for f of x equals 2x squared plus 3, make a table of values and look at finite differences. All right, so we're going to make a table of values. We'll use -2, -1, 0, 1, 2, and 3. That's enough. These are evenly spaced. They're going up by 1 every time. So to find my y values, I'm just going to substitute in. -2 squared is 4, 4 times 2 is 8, plus 3 is 11. -1 squared is 1, 1 times 2 is 2, plus 3 is 5. 0 plus 3 is 3. 1 times 2 is 2, plus 3 is 5. 2 squared is 4 times 2 is 8, plus 3 is 11. 3 squared is 9, 9 times 2 is 18, 18 plus 3 is 21. So far, all I have are my x's and my y's. These are my x's, these are my f of x's, or the y's. Now we're going to look at our finite differences. So here's what we do. We're going to look at these two, and I'm going to subtract them. Always the second minus the first. 5 minus 11 is -6. 3 minus 5 is -2. 5 minus 3 is +2. 11 minus 5 is 6. 21 minus 11 is 10. These are what we call our first finite differences. Notice how those are not all the same number. So what that tells me is that this function is not x to the first. This is not a linear function. In this case, we already know what it is. What is it? It's quadratic, isn't it? We're given it. But let's look at our second differences now. I want you to notice this. -2 minus -6, that's 4. 2 minus -2, that's 4. 6 minus 2 is 4. 10 minus 6 is 4. These are all the same. These are my second finite differences. So I would know, based off of these numbers all being 4, I would know that it would have to be a quadratic function. And it is a quadratic function. We were given it this time. Okay? Any questions there? If these had not been the same, then I'd have to keep going. Let's turn the page to page 120. We're actually going to go down here to 5 and 6 first, and then we're going to go back up to number 4. So let's look at these. It says, for numbers 5 and 6, use finite differences to determine the degree of the polynomial function that fits the data. Then use technology to find the polynomial function. All right, so we're going to look at our finite differences. -6.5 minus -14. That would be what, 7.5? 0 minus negative 6.5 is 6.5. 5.5 minus 0 is 5.5. This would be negative 4.5. Or no, that's 10, not 1. That's going to be positive 4.5. 13.5 minus 10 is 3.5. So those are our first finite differences. I take a look at those. They're not all the same, so I know it's not linear. So now I'm going to check my second differences. So 6.5 minus 7.5 is negative 1. This is negative 1. This is negative 1. This is negative 1. So now I would know my second works, so it has to be a quadratic function. We were then supposed to use the technology to find the polynomial function, but we'll just wait and do that on the next one, okay? So let's look at number 6. 4 minus 30 is negative 26. 0 minus 4 is 4, negative 4. Got to be careful with these. 0 minus 0 is 0. Negative 14 minus 0 is negative 14. So the first finite differences does not work. It's not linear. Negative 4 minus negative 26 is 22. 0 minus negative 4 is 4. Negative 14 minus 0 is negative 14. It's not quadratic. I go to the next level. 4 minus 22 is negative 18. Negative 14 minus 4 is negative 18. There we go. So it wasn't linear, it wasn't quadratic, it's cubic. So once I know what kind of data I have, I'm not going to have to waste time when I go to calculate. So we're going to go to Stat, Edit. We're going to go up to the top and clear. Put in our x's, negative 2, negative 1, 0, 1, 2. Put in our y's, 30, 4, 0, 0, negative 14. We're going to, let's take a look at the data. To take a look at the data, I have to turn on my stat plots. I can just go to y equals, go up to plot 1, turn it on, clear out anything I've got in here. I can now do a zoom stat. That's going to allow me to see my data points. And I can see that these do look cubic. So now I can go to my stat, calculate. I go down to my cubic regression. I'm going to have it go ahead and store it. You can go to vars, yvars, but guys, here's a fast way too. Go to alpha trace, and it'll bring up y sub 1 for you to store it. And then you can go down to calculate. Did I go through that too quickly? Okay, I'll go back to it here in just a minute. All right, so let me do it again. I went to Stat, Calculate. I went to Cubic. I want to store it. Now, like I said, you can go to vars over to, let me show you this way. You go to vars, yvars, function, y sub 1. That's one way to do this. But I was showing you a shortcut way is to go to alpha trace, and it brings up y sub 1. And guys, don't be afraid to check these. These are shortcut menus. This F1, F2, F3, F4. Take a look at those. I'll show you in a minute some other things that can do. Everybody here now? Go to calculate. Here's our function. I'm going to write it down. It's y equals, now it's telling me that a is negative 3, x cubed, plus b is 2, and that's x squared. C is 1, and that's x. And then my d value is just 0. And r squared is exactly 1, so this should be a perfect cubic function fitting through my data. So now when I hit graph, see how that cubic function fits through there just perfectly. Okay, questions there? Guys, have I shown you these shortcut menus before in here? Okay, go to alpha F1 real quick. This is kind of cool here. If I want to put in a mixed number, go down to number 2. Watch what it gives you. I can put in 2 and 1/3 plus, oops, hold on, I got to get out of there. Arrow over, plus, and now I can go back to there. 5 1/4. Enter. And it gives me the number like this. But suppose I want the number as a mixed number. So then I can go back to alpha F1 and I can push this. I think it would be this one. So this is going to take me to n over d to this form. So if I push that, and then it changes it to mixed number form for me. Kind of cool things. So check those out. You'll be impressed with some of the things you can find under all these shortcut menus. Okay, now let's go back up to number 4. Write a cubic function that passes through the given points. I can do this on my calculator, but I don't really have to, so I'm not going to. This is a cubic function, so it has to be y equals a. What would this factor be? Everybody? If negative 2 is a 0, what was it as a factor? X plus 2. Here's another 0, so it would have been what? And then here's another one. What would it be? X minus 3. Now, there is going to be some kind of a coefficient, and I don't know what it is. But see how I know another point that's not a 0? 0, 3 is not a 0. It's a y-intercept. But I know that point. When y is 3, x is 0. So I'm going to plug in that point. So now I'm going to have 3 equals, this is going to be negative 3 times negative 1 is 3. 3 times 2 is 6a. So a is going to be 1/2. So here's going to be my function. And this is going to be my function in factored out form. And that's totally fine to write a function in factored out form. You don't have to multiply it all out. Okay? In fact, this kind of form is actually more helpful than having it multiplied out, because isn't it easier to graph it when it's in this form? Yeah. All right, one more problem, guys. Flip over here to number 10. The table shows the value y in thousands of dollars of a signed autograph of an MVP football player where x represents the number of years since 2000. Find a polynomial model for the data for the first 5 years. Use that model to estimate the year the autograph will be valued at $5 million. That should be a period, not a question mark. Okay. So let's go ahead and do this. We're going to look at our first differences. What's that going to be? Negative 28. And sometimes you do this a couple times. This is 128. Yeah, thank you. So we're kind of thinking as we go here. Okay, we know it's not linear. I'm just going to check for quadratic. I'm not going to go much further than that. This would be 100. $220. $398. Okay, so it's not quadratic either. So what do I know it's going to have to be? Cubic, but it could be also quartic. Okay, I'm not going to bother going any further. I can kind of already see it's not going to be cubic. It's probably going to be quartic. But I don't even really have enough data to know that, so I'll show you what we do in this case. We're going to go to our stat, edit, clear it out, put it in there. Here's what we do when we're not sure. First of all, I want to see my data points. I have my stat plots on. I'm going to do a zoom stat. I can see these points. This might be cubic. It might be quartic. I'm seeing my old function. I didn't clear it out yet. Clear it out. Okay, so I'm going to go to stat, calculate. I'm going to see if it's cubic, even though I really already know it's not. I'm just going to calculate it. And look at my r squared. It's 0.999. That's pretty good. We'll see if we can do even better. Let's go to stat, calculate. Now let's check and see if it's quartic. So I go down here. All right, look at that. R squared is exactly 1. So that tells me that it is exactly a quartic function. Now, here's some things you have to know about this. So my quartic function is going to be y equals 2x to the 4th. What is this number here? 0. What's the next c value? 0. So it's going to be 2x to the 4th minus 2. Now I got to think of what power this is. This is x to the 4th, x to the 3rd, x to the 2nd. This is just going to be x, and this is just going to be my constant. The calculator tries to be real exact, but it's actually making things worse with all these places it goes out. I'm going to type this in myself. All right, so we're going to graph that. Here's our function. So we have the equation. We've got that part of it done. And then the last thing it asks us is, use the model to estimate the year that the autograph will be valued at $5 million. Well, this is in thousands. How many thousands is this then if it's 5 million? 5,000 thousands would be 5 million, right? Okay, so I have to go to y equals, and I'm going to have to put in 5,000. If I want to be able to see 5,000, I got to make my y max go up to 5,000. I might want to make it even 6,000 just to be sure I see it. I needed to make my x's go further too. Okay, so let's change our window again. Let's make our x's maybe go up to 12 years just in case. There's our quartic function. Here's 5 million. And I want to find out where those are equal. So second trace, find that point of intersection, get kind of close to it, enter, enter, enter. And is that 6 or 0? 7.07, I think. So it's 7.07 years past 2000, is it? So it would be then in 2007, it will be worth, or it was worth, I guess we should say, $5 million. Okay, makes sense? All right, good stuff there.